Let me pull this over. Yeah, this is base 2 logs. I'm going to pull a little Wolfram Alpha action over here just so we can take a look at it.
If you don't, it's base 10.
That's still my right.
Or if you put more gooder.
Yeah, I know, right? It's L space G, same thing.
There we go.
He's like, no, I'm doing it my way. Stop pressuring me.
Okay, so you got 2 log 2/36 log 36 plus 4/36 log 2 18 plus we're missing the 3 out of there.
Out of where?
Right? You got
3.
Oh, just
you got
tack it
1,
on.
2, 3. Well, no, that's
Hey,
what. Okay.
the don't forget to do number 5 of the homework is covering it. That's the problem.
Yeah. Yeah, exactly.
3 log.
2 times. Whoops.
3 over 36 log.
Yeah.
36 over 3. Yeah.
3/36 log 2 36 over 3. Okay. All right. So, or in other way to do that, just pull the 1/36 out front, and then you've got 2 log 36 plus 4 log 18 plus 6 log 36 over 3 plus 8 log 36 over 4 plus 10 log 36 over 5 plus 6 log 36 over 6, right? And that comes out to 3.27, and little nod to Major Yarborough, 4.4. Okay, everybody see how this is just, this whole thing is just the sum of P log 2 1 over P, where the probabilities are 2/36 for 1 and 12. Well, 1/36 each times 2, right? 2/36 for 2 and 11. 3/36 for 3 and 10, and so forth, up to 1/6 for 7. Okay, now, so we end up with 3.27, right? Assuming you managed to type this into the calculator or Wolfram Alpha correctly, which I didn't at first. Apparently, opening and closing parentheses matter. Who knew? All right, so now the next step is, what's our minimum average code length that we could use to send these results? Well, 3.27 is the minimum. Yeah,
H and then H plus 1.
Okay. Right, it's somewhere between H and H plus 1, right? So it's someplace between 3.27 and 4.27. But we could do a quick tree really quick. Let's see. So here we've got 2. Yeah, sorry. I know, I heard myself say that, Matt. Can we edit this later, Justin? Please. Please. Okay, so normally you put them in list of probability from highest to lowest, right? So 7, 6, 8, 5, 9, 4, 10, 3, 11, 2, 12, right? I just reordered these in highest to lowest probability. So the highest probability, let's just do it in 36. 6/36, 5/36, 5.
Got it.
Okay, well, we need to write them down just so that.
No, we don't.
I think
I'm just kidding.
my outline.
Don't mind me. Don't mind me.
And my intervals.
Peanut gallery.
Right, 6, 5, 5, 4, 4, 3, 3. Yeah. 6, 6,
Should be helping everybody out on roulette.
What's that?
Should all be helping people when they play roulette. Or,
Yeah.
craps.
Yeah, this is craps. This is good for your crap.
That would be if you change the order. If order.
Okay, so the two lowest
One roll, then another.
probabilities are 1/36.
It's not so much that 1 and 3 and 3 when you're switching, it's that it's actually.
Now we can
possible
do this a couple
that you
different
roll
ways.
1 and a roll 3. You have roll 2,
I'm
roll
gonna do
2,
these
that's
two.
never happened with 2 rows.
4/36, and now these are 5/36, right?
Oh, so you gotta do the 2 and the 3? Oh no, that's right, I'm sorry.
Now I've got to do the 4
3
and
and
the
the
3.
4. Oh, I would have done so that way you don't cross over.
Well, we're gonna have to cross over at some point. Wait, watch this. Either way, you're gonna end up crossing over. So 2/36. Let's put these two together then. Here's 4/36. Now our lowest ones are 3 and 2. So somehow we've still got to cross over. 5/36. Now 3 and
3 and 4.
4.
736.
7/36. Now we've got
4 and 4.
4 and 4.
4 and 4.
8/36. Now we've got
5
5 and 5. 10/36. And now we've got 7 and 5. 7 and 6. No, 5 and 6. 11/36.
87. Oh, you just had it cross it.
13/36.
11 and 7. Oh, dude.
21/36. And
And you added something wrong.
I added something wrong.
2 and 2.
All right,
3 and 2
2, 2.
is 5.
1 and 1 is 2. 2 and
8 and
2.
7 should be 15.
Oh, thank you. All right, there we go.
And you added
At least it was
something.
close to the
I didn't have
end.
1336. I was like, where did that come from?
All right, and so now here is
1.
my 36/36, right? Okay, so now let's do 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. 0, 1, 0, 1.
On the midterm, 5 dice.
5. Yeah.
I don't have that much paper.
Okay, so. Sorry, Captain Wilson, I'm going to erase this.
You would.
Okay, so this top one here is 1, 0, 0. The next one is 1, 0, 1. The next one is 1, 1, 0. This one is 0, 0, 0. And 0, 0, 1. Then 0, 1, 0. Then, let's see, 1, 1, 1, 0. Here is 0, 1, 1, 0. This one's 0, 1, 1, 1. And finally 1, 1, 1, 1, 0. 1, 1, 1, 1, 0, and 1, 1, 1, 1, 1. Okay, does it meet the prefix property?
Looks like it.
Sure. Well, does anything start with, okay, nothing starts with a 1, 0, 0. Nothing starts with a 1, 0, 1. Nothing starts with a 1, 1, 0. Yep, it looks like it works, okay? So there's a Hamming code. You saw already we could have, a lot of them were equal probabilities, so we could have picked a bunch of different Hamming codes, but they should all come out with the same average code length, because that's all we really care about. So now we've got 3 times 6/36 plus, well, actually, let's just add up all the probabilities of length 3, okay? 6 plus 5 plus 5 plus 4. 6 plus 5 is 11.
27.
Okay, so 27 36ths. 27 36ths plus 1, 2, 3 of them are 4, so 4 times 7 36ths plus
5 times 2.
5 times, what are they, 2 36ths? And that equals what?
You watch it, type it in, see if you get it right. It's funny to watch it.
82, 92 over 36.
Times 27 times 3 plus
119.
4 times 7 plus 5. 7 plus 2.
3 times 27, 81, 28, 109, plus 10 is 119.
Yeah, 119/36 is what I got. So that equals 3.305.
Which is greater than 3.27, but less than 4.27, so it's just a little.
He started at the bottom. He did 1 and 1. He got 2. And then
Oh, yeah,
he had
just did 119.36 and had it solved.
All right, and you notice as we start getting more things on here, we start approaching that lower bound a little more. Well, and also because a lot of these had equal probabilities. The more equal the probabilities are, the closer you can get to that lower bound. And also the more that you do, the closer you can get to the lower bound.
If that has to be between h and h plus 1 to be what that.
To be optimal.
To
I
be
mean,
optimal.
yeah, there always is one.
3.27, and so the 4.27 is just h plus 1. And because it's between those, it's out.
Right. Here, we'll put this on here. H.
Hey, don't skip steps.
H plus
I
1.
know, jeez, come on.
Average code length. There we go.
Wait, huh? You flip? No. I'll stay, wait a minute.
flip one of the inequalities.
No, he didn't. It looks like it, but he didn't. It's funny when you look
I was
at
looking
it.
at 7.
Yeah.
It does look backwards.
Yeah,
It is backwards.
Okay, now we know why it looks wrong. I was like,
Yeah.
wait a minute, how
I'm
can
like,
h
wait,
be
wait.
bigger, but then h plus 1 be less than?
Sorry.
One of those negative values is.
There we
I don't know
go.
why it looks funny.
That's the problem is I'm facing this way, so great.
Oh, yeah.
To me, it was right.
I'm with Christy, I think, yeah.
All right.
Video editing.
Step back one, the 3, 27, 36, 4, 7, 36. Run through that step again.
Okay, sure. This was, all I did is,
Whether you're counting.
okay, I did 3, every one of these that had a code length of 3, I summed the probability, which is
Okay.
6 plus 5 plus 5 plus 4 plus 4 plus 3 plus 3, 36, which ends up being 27/36. Now, I could do this out the long way and just do it one by one. 3 times 6/36 plus 3 times 5/36 plus 3 times 5/36 and so forth. I'm just pulling it together. And then all of the ones that had a code length of 4, we just added there 3 plus 2 plus 2, 36. And then all of them that had a code length of 5, 1 plus 1, 36. Okay, so what, other than just giving you something fun to do with your calculator, what's the point of all of this? What's that? To torture? Yeah, that's pretty much it. I mean, this is kind of the 24 officers version of AIT. You're doing some pointless task for no. All right. No, why is this important? This tells us that if we have prior knowledge of the probabilities of something occurring, we know there's a minimum value of number of bits that we will need to send, right? We also know the maximum value that if we're sending more bits than h plus 1, we're wasting bits. So we could come up with a better code to encode it. In practice, the way this works is instead of going through this whole process and doing a Huffman code is the ideal thing. It's kind of like an isotropic antenna. It's out there and it's well, isotropic antenna is not possible, but it's ideal, but it's not very practical. You don't do this every time. In practice, what we normally do is put together a code book based on the estimated probabilities of things. How can we find out the, let's see. So if we just want to take straight English and have the best code book to send English text, that's, oh, that's not what I wanted it to do. Apparently it's looking up the number of people named English in the United States today, which it's not. There's no data available. Wait, somebody give me 2 of your first names. Nicholas and Nick. All right, Nicholas and Nick. And it's gone. Oh, wait. Okay, Nicholas is the 42nd most popular name in the U.S. right now. 1 out of every 236 people is named Nicholas. Nick is less than 1 in every 12,500 people. There are 8,500 Nicholases born every year. And wow, look at this. So here's the cool part about it. This is Nick. Nick actually seemed to have peaked in the 1920s with a slight resurgence in the 1960s, but Nicholas really took off about 1980. You know, and now everybody's starting to. And so here's the average age of people named. The most common name of people named Nicholas is 15 years old. Most common age of people named Nick is 50 years old. And here's the distributions too. All right. Anyway, okay. So what we were trying to do, let's do it. It didn't get it. English language table. Well, it's not. The thing is, it's not the same for every language that uses the Roman alphabet. That's the. So, English letter frequency table. That's what I should have. And there are a bunch of different frequency tables, but here, this is out of a sample of 40,000 words. The frequency. This is apparently in percent. The letter E is the most common letter, with a frequency of 12%. So you can see how now, if we wanted to do Huffman coding, look at this. Now we have our a priori our probabilities, right? In English. So in English, in this particular 40,000 word sample, it was ETA, OINSR were the most common ones. Different frequency tables get that slightly differently. But now this gives you a percentage. If you're trying to do English and making a Huffman code, we've already got the probability. So you could take this right now, given what you know, and write a Huffman code that would work for English, right? This is a midterm. Yeah, no. You could. I mean, 26. We just did it with 12, and it was kind of big. So it'd be about twice that many.
What was the sample size of 40,000 based on?
Well, that's a good question. This is, I'm not sure which one this is. This one's one out of Cornell. There's a
40,000 courses is almost nothing.
right.
So there's gotta be
Well, there's a bunch. I mean, if you go into the some of them are based on, you know, like there's some that are based on Shakespeare's works, and there are some that are based on like newspapers, and they're significantly different. If we look at letter frequency here, we'll go to the font of all knowledge. If we're trying to come up with these a priori probabilities, okay, so accurate average letter frequencies can only be gleaned by analyzing a large amount of representative text. With the availability of modern computing and collection of large text corpora, such calculations are easily made. So here's, yeah, they've got one that's press reporting, one that's religious text, one that's scientific text, one that's general fiction. So even just in English, it varies, the probabilities vary depending on what kind of English it is. So when you're doing this, yeah, F is the no. So this, I mean, you can go through this with and then different languages. So here's the this one. E is 12.702, which is about what we saw. T 9.056, then A 8.167, and so forth. Then you can do first letters of a word, and then here's, okay, so now here's frequency tables for other languages: French, German, Spanish, Portuguese, Esperanto.
It's not real language.
Italian, Turkish, Swedish, Polish, Dutch. What about Japanese and Chinese and so forth?
It's different.
It's totally different because they're,
Character based.
yeah, it's character. Well, Japanese,
Japan, Korean are all actual letters, but
Chinese is still just character based, and then now if they write it out in pinyin, then it uses Roman letters to spell it out, but you can't tell what.
Romanization for.
Yeah, and you can't tell what character it's talking about, except from context. So yeah, that ends up being totally different. But for most of the things that we would want to send and compress, we can compute a priori probabilities. That's the worst part of trying to come up with codes that get close to the entropy, is coming up with those a priori probabilities. For English language, we can do it. What about for like images and things?
Let me do it based on percentage of pixelation or the radius and closure.
So, yeah, I mean, it depends. It depends how you do it. There's a bunch of different ways. We can break it up into morphological patterns and send a code for a particular pattern and then just attach a color to it, or we can do it we can compress it by colors, or then you can add run length encoding. I mean, there's all sorts of stuff to add to this. This is the very, very simplest basic way of compressing this, but for symbols at least, this Huffman will result in an ideal, or at least an optimal code. I don't know if it's ideal or not. Depends on the situation. Does that make sense? So when would you use this in your job? On the midterm, exactly. Yeah, in practice, you're probably not going to do much with this. The main point behind it is to recognize that you've got, what compression is doing, why it's there, what the magnitude of your possible compression is, and things like that, so you can recognize what things could be improved in a communication link. I mean, would increasing the compression help with the link? Well, if you're just sending zip files over it, there's really not much you can do for further compression in the link itself, right? What we're trying to point out here is that there is a lower bound, and if something is already compressed, You can't just say, heck, let's compress it again a different way. It's not going to do much, right? There's always that lower bound of the entropy. Okay, then what we'll do is take a quick break.